Stanford. He's going to be telling us about finding Milli-magnetic charged particles.
Thanks, happy to be here. So yeah, today I'm basically going to be telling people how, about some bounds on magnetically charged particles. It's some work in progress with a graduate student at Stanford. So the basic idea behind particle physics, right, is basically we're trying to find new particles. They can be particles that make us up, right, like the quarks and leptons. They can be things that mediate forces, like photons, gluons, etc. But this has essentially been what, at least the pheno part of particle physics has been all about. So if your goal is to look for particles, right, there are basically two ways to do so. There are two broad types of what new particles are going to be. They can be heavy, which is essentially that they've just been too heavy for us to produce so far. That's why we haven't seen them. Or they can be light but weakly coupled. And so that's essentially that we have the energy to produce them, but because they're weakly coupled, they're hard to produce, they're hard to see. And so broadly speaking, these are the two categories of new particles. And so since the goal is, of course, to find them, how do you find these guys? Well, if they're heavy, you just go to higher and higher energies, right? You just dump more and more energy into your experiment, and eventually you'll have enough energy to produce them. Fine. They could also be light but weakly coupled, but then here, the problem to producing them was that they were weakly coupled. And so you have to just do the experiment many, many times. You have to have high intensity, high luminosity to see these guys. So the way we've sort of seen these heavy particles is extremely simple, right? You just take things, collide them at very high energies. This is what the LHC does, and they collide protons at high energies. And it's very nice at high energies because at high energies, things interconvert very easily. There's no real difference between colliding protons, gluons. You can even bound like leptonically charged particles, and etc. And so to zeroth order, it doesn't matter what you collide. You just collide things at higher and higher energies, and that's good. And then the particles you produce, it doesn't really matter how they couple. You just produce them with pretty large cross sections regardless. So the situation is very different for light particles. The reason why is that at low energies, things are different because conversions between particles are rare, right? It matters a lot whether or not the thing we're looking at is an electron or a muon, like protons versus neutrons, et cetera, et cetera. And then not only that, but how they couple are also pretty important, right? If things are coupled like a gauge charge because of E&M, or if they're coupling because of dipole moments or Yukawas, all these things look very different, and you could be looking for something that sees dipole moments and then miss Yukawa couplings and whatnot. And so because of this, producing heavy particles, you just bang stuff together at high energies, but for light particles, you need, there are many very different options, so you have to just do many different types of experiments. So very briefly, I'll sort of describe some of the experiments people have done to look for light particles. The sort of simplest thing is you take any of these high energy colliders and you just run them for a long time at high luminosity, right? You can have high intensity colliders. This is sort of, I showed the example of SLAC, but they do that for like Babar and whatnot. And so it explores things that are sort of weakly coupled to protons, electrons, sort of depends on what you're scattering. Another type are beam dump experiments. These are pretty simple, right? It's literally, everything is in the title. You take a beam of particles which you've accelerated, you just dump it on some sort of target. This is an example of a SLAC experiment where they took electrons, they dumped it on aluminum, and then, remember, we're looking for light and weakly coupled guys, so they just put a huge amount of dirt to block all the standard model particles, and then anything that's weakly coupled, light but weakly coupled, will fly through and then eventually has the possibility of scattering at some detector downstream. So, okay. Of course, anything that we do, nature does better. So you can also go to very high densities in astrophysical objects. So sort of the highest density objects out there are sort of neutron stars, red giants. Well, red giants aren't that dense, but neutron stars and supernova are definitely very dense. And so the way you sort of can constrain new light but weakly coupled particles is, for example, things like cooling. So this is the standard supernova argument that if you produce new particles in a supernova and you start carrying away too much energy, you can prevent the supernova from happening. And things like stars, we actually understand them very well. So like red giants, there's actually, the better constraint comes from energy transport, because we actually understand how energy is transported from the inside to the outside well enough that even things that don't quite escape the star, so aren't a source of cooling, can be constrained. Of course, there's also the option of having things produced as stellar objects and then observed on Earth. So that's, for example, axions that couple to just photons. That's their strongest constraint from supernova. Another high-density object is, well, possibly a high-density object is dark matter. So there's a huge amount of energy density in dark matter. That's like 0.3 GeV per centimeter cubed. So if dark matter was GeV or less, there's at least one particle of dark matter per centimeter cubed flying through us. So that's a huge flux of dark matter. And so we could try to imagine looking for it. And so there are various experiments. One example is Xenon 1 ton, where they just look for scattering of dark matter off of the nuclei. And sort of final example I'm going to give of how we look for light weakly coupled particles is sort of examples where dark matter has a macroscopic size. So if you imagine, don't treat dark matter as a particle, but as a wave flying through us, and if this wave takes macroscopic time, for example, let's say 5 seconds to pass through us, then you can look for time-dependent processes. So if it couples, for example, like a dipole, or if it couples like charge or mass, you can use, for example, very high precision clocks to constrain dark matter. Okay, so there are many different types of scenarios, and when there's so many scenarios, you need some sort of way to organize it. Okay, right? You want to start with the simplest stuff and then sort of expand away from there. And so what is sort of the simplest scenario? Well, I'd say the simplest scenario is we're looking for a new particle, but it has like the old interactions, right? What are the old interactions? Well, they're gravity and E and M. I'd sort of argue that this combined with the other flip of old particles with new interactions, which are fifth force, are the two simplest cases of looking for new particles, or at least light but weakly coupled ones. And so I'm going to be focusing on a new particle with old interactions. And so, well, old interactions, well, it definitely couples to gravity. What about E and M? So what about new particles that carry charge and mass? You mentioned this to particle physicists, and we'll flash some plot like this and be like, well, here's the charge, here's the mass. We have some huge constraint on Milli-charged particles, right? You can see sort of the stuff I mentioned here, of like red giants, supernova, like various accelerators and beam dumps and whatnot. But implicit, when we talk about Milli-charged particles, at least in the past, people really just talk about electric charges. And so, but of course there are two types of charges under E and M, right? Electricity, and there's also magnetism. So what about millimagnetically charged particles, right? What do we have to say about them? So the outline of my talk is basically going to be, well, I'm first going to talk about millimagnetically charged particles. Essentially, why haven't we talked about them before? How can they exist? And how reasonable is it to expect that they exist? I'll talk about some constraints that we'll be placing, and then finally I'll conclude. All right. So if you talk to people about magnetic charges, they're very happy with the idea that monopoles can exist. But when you mention millimagnetic charges, people tend to get confused. And so what is the source of this confusion usually, right? Why do people not think about small magnetic charges? Well, the answer is it's usually due to the quantization of angular momentum. So let's go back to this story. So you can go give an undergraduate this problem, which is take an electrically charged object with charge QE, put it some distance n away from a magnetically charged object with charge QM, and just say, what is the angular momentum in the E and M field, right? So then after some time, they'll sit down, calculate this integral that they sort of saw in probably freshman year E and M, maybe second year. And then after some toil and trouble, they'll eventually spit out this answer, which is just the product of the charges up to some order 1 number. So now, once you know quantum mechanics, you know that angular momentum is quantized. It's quantized in units of h bar over 2. So if you just choose this sort of value for g, the sort of electric charge, it's off from 2 from what a lot of people use, but I'm doing that just to give so that things are integer. What you see is that basically quantization of angular momentum says that the angular momentum is equal to, or the product of the charges is equal to an integer. So in other words, because the electron has charge 1 here, monopole charges are quantized. And then so people just say, well, it's quantized, let's look at the smallest charge allowed. And so that's what people have been doing mostly. And so, okay, that's nice. But of course you know that this is not cannot be completely correct. At least there must be ways around it. And the reason for this is, think about the following. People usually talk about electric charge being quantized in units of E, but in fact, things like quarks have charges of 1/3. And so it's clear that there is a way around this thing, this sort of argument. And so let's sort of explore what are the ways that are even realized possibly in nature around this. And so the simplest thing to do is, well, okay, you had one E and M. Now let's say you have more than one force, right? Because, for example, the way the quarks get around it is because they have things like QCD. So now let's add two U1s. Let's not go all the way and add an SU3, but let's just put in another U1. So let's say I have two U1s. Then if you repeat the argument for the quantization of angular momentum, what you find is that the sum of the product of the charges is an integer. So in other words, it's perfectly okay for two different guys which have sub-minimal charges to just have the product be added to give you an integer, but each individual guy, let's say like Qm, could be some small charge epsilon. In particular, what you can do is just, if you just wanted to claim a charge assignment, and in fact this is the one I'll try to motivate later, is you could say that, well, here's an example of a case where the sum is an integer, but the magnetic charge is not, which is if you have an electron with charge 1 under 1U1, epsilon under another, and a monopole with charge 1 under the other guy, and minus epsilon under us. So obviously the sum of the products here, right, minus epsilon plus epsilon is 0. And so you have quantization of angular momentum. Okay, so hopefully, so like as I said before, this should not actually surprise us that much that it's possible to get around it, that you can choose charge assignments to get around it, because quarks have fractional charge, and we still talk about quantization in the units of E and not E over 3. And so in fact, we will evade, if you try to construct a physical model of this, which I will do in a second, you'll evade these constraints by the exact same way QCD does. In particular, all finite energy objects will have quantized magnetic charge, right? This is the statement that like protons and neutrons all have charge 1, or multiples of 1. And you'll also find that the Dirac string becomes a physical string. So QCD, which is not a problem either, because obviously quarks have strings attached, and we don't care about that. So these same two things will actually be what's responsible for escaping quantization of angular momentum in an actual model. Okay, so I sort of argued that it's possible to write down some charge assignments which evade this quantization argument, but
can I just want to make sure I understand this quantization business.
Yeah.
I know I don't usually think about this. So what is it that controls, makes things multiples of E? I mean, how is E coming into this argument? Because I can rescale E and rescale Q. So
Yeah.
I'm just confused about this basic point.
So essentially, right, you can write the correct quantization has the product of E and Q and G and Q.
Right.
So obviously you could rescale E and rescale Q. And so what
So
people
E is
just
just-
conventionally say is the electron has charge 1 and use that to define E. And so that's how people just define E, separate out E versus QE. They just define the electric charge of the electron to be 1.
But then, okay, then can you just maybe, I was somehow confused about your U1 cross U1 example.
Yeah.
There, when you're given the values in the table, those are the values of the couplings in units of E.
Yeah, so like here I said the electron had E equals 1, essentially.
Right.
And for the monopole it had G equals 1. Which then means that G for our sector is 2 pi over this guy, and E for their sector is 2 pi over that guy. So it shouldn't bother you too much to use an electron to set G equals 1 and a monopole to set G equals 1, because when you define the electron to have E equals 1, you've also implicitly assumed that it's electric rather than magnetic. And there's electromagnetic duality. Everything in our sector, we could have said everything is magnetically charged and there are no electric charges. This is just a convention that we chose everything to be electrically charged and not
And
magnetically
here all
charged.
the EI, BIs are all zeros, so there's no necessary connection between this epsilon and minus
They have to be
epsilon?
because the product, the sum of the products is an integer. And so the only way for this product plus this product to be an integer is if these two epsilons are exactly the same.
Okay.
And this will actually happen for a simple thing like kinetic mixing and whatnot.
Mhm.
And so when you actually write down a consistent QFT, you'll naturally get this exact relationship. You'll get exactly the minus sign, and that these guys are both exactly the same.
Mhm.
And so I'll do that in a bit.
Okay.
Okay. So let's sort of now claim how plausible this scenario is, right? Because as Marcus just said, these guys have to be exactly the same. And so you might imagine this is a really weird charge assignment. Is this actually natural to have something that looks like that, right? And so the thing you might argue about is that, one, these fractional charges, how natural is it to have an epsilon there? That's not an integer. How is that natural? And how is it natural that the two are exactly the same up to a minus sign? And the other will be this argument of like, well, people usually don't like monopoles at low energy. So how plausible is it to have a low energy monopole? So let's first...
By low energy, do you mean low mass?
Low mass, yeah. So in particular, the case I'll be talking about later will be like masses of GeV or smaller. But yeah, I'll get to that in a bit. So let's first talk about the fractional charges, these epsilons that look a little weird. And so the easiest way to see this is just to write down kinetic mixing. My claim is that if you just write a theory with kinetic mixing, you very, very naturally get the theory I just wrote down before of these two epsilons being exactly the same up to a sign. So what is kinetic mixing? It's just, if you take our U1 and their U1, you can write down a term that literally just mixes the kinetic terms for our U1 and a U1 dark. And motivated for reasons I'll tell you later, but we're going to add a mask to this other guy. You might imagine that this needs to be a mask because of things like VBN and N-effective constraints, but I'll get around to this, why this mask term needs to be added later. Okay, so let's see if I can convince you guys that kinetic mixing naturally gives you this epsilon charge. And so when talking about monopoles, the Lagrangian is not a very useful object because monopoles are sort of non-perturbative or extended objects usually, or you have to write down a non-local theory. So let's just write down Maxwell's equations. Okay? So here's Maxwell's equations for kinetic mixing, right? Normally, you have just the divergence of the E field being some current. So that's this guy. It's true for us. It's true for them. And then we have no monopoles. They have a monopole. And then kinetic mixing is just the addition of this epsilon part in the kinetic term. So if you take this Lagrangian, write down Maxwell's equations, you get this guy here. Okay, so let's manipulate Maxwell's equations. You'll notice here that there's a mass term, and we know that our photon is not massive. And so what we have to do is do a field redefinition to get rid of the kinetic mixing in a way that does not make our photon massive. So the simplest thing to do is to shift our photon by an amount epsilon times A dark, right? So in particular, this is the field redefinition. These are Maxwell's equations. And you'll notice that it does things like get rid of these epsilon kinetic mixing here. So let's do this field redefinition onto this guy. And these are Maxwell's equations now. You'll notice that our electron is charged 1 under the photon. That's good. You'll notice that it also happens to be, for the dark photon, there should be m squared there. But okay, that they have their dark electrons, but that our electron picks up a small epsilon charge under their dark electron. And so this is exactly the case that I sort of mentioned before of like a 1 epsilon. So kinetic mixing, because it mixes our E field with their E field, makes our electrons epsilon charged under them. But you'll notice now that because that field redefinition now makes their monopoles minus epsilon charged under ours, RU1. And so their monopoles have naturally picked up a minus epsilon charge under our magnetic field. So kinetic mixing does literally this, with exactly the minus sign, with exactly the 2 epsilons. And because the F dark, us, can be some arbitrary number, doesn't have to be an integer. In fact, if you generate it through loops, it'll RG run, it'll be non-integer. And so it's very natural for this guy to be non-integer and exactly this scenario. This is exactly what's predicted by kinetic mixing, which is nice and should not surprise us that kinetic mixing preserves quantization of angular momentum. Okay, so that's fractional charges. So anything with kinetic mixing gives sort of monopole charges exactly the way I described. So I would say right away then millimagnetically charged particles should be pretty clear, right? Because if some dark sector had a monopole at low energies, it could mix. Kinetic mixing is what we always do, and it becomes epsilon charge under us. So then, okay, the other thing that will bother a lot of people will be like the idea of having low energy monopoles. So why is the...
Pause for a moment. So if you have a standard Millikan oil drop experiment and you measure E, the E that you see then is actually not the real E?
So then
fundamental before the mixing?
It'll depend on which distance scale you're looking at. So if you're at if the mass of the n, if you take the limit where m goes to 0, that is correct. The force you see is not that. But as you take m to infinity, the electric field in the other sector gets damped out extremely quickly, and then what you're measuring is actually just the E of the other of our sector. And so it's an issue of when you probe the charge of the electron, at which scale are you probing it at? And that's actually one of the constraints that will pop up on these theories.
Okay.
And because obviously, if you look at the force between 2 electrons and you just vary them very close to very far, you can look to see is there this additional force that's exponentially damped.
Okay.
And it turns out actually that's going to be weaker than the constraints I'm going to mention later, which is in some sense surprising because we can really measure that pretty strongly. Yeah. Okay, so next is the idea of monopoles at low energy, right? I've been sort of treating these guys as monopoles, and there's really a strong theory bias that monopoles should not be present at low energies. And so the reason for this is essentially, well, it's really just a theory bias in some sense, right? Because just Polyakov monopoles were first discovered in sort of gut theories where they were very heavy. But because this guy is a monopole in a different sector, its gut scale, its unification scale, could really be at any value you want. And so it's perfectly okay to have its monopoles be very light. But I thought it would be even more amusing to phrase the entire theory without monopoles. So I'm going to now talk about the entire thing with just electrons and show how you can do the exact same thing with electrons. So what you can do is really utilize the fact that there's electromagnetic duality. So in other words, what you call the electron is completely arbitrary, or in some what you call the charge of the electron is arbitrary. You can call it magnetically charged, you could call it electrically charged, you could call it some combination of the two. The Maxwell's equations are completely invariant to this, essentially a rotation between the E and B fields. So what you can do is utilize this sort of rotation on the previous example and say, I have a fundamental electron in our sector, and call that their monopole now a fundamental electron of their sector. Now, instead of the standard kinetic mixing, what you have is electromagnetic mixing, right? So what you have is a mixing between our E field and their B field, their B field and our E field, or their E field and our B field. And so you see that now we're mixing the electric and magnetic charges. And so now you can't even make the argument that monopoles should always be heavy because their guy you're just treating as an electron. And instead the mixing is, instead of with E and E and B with B, is E with B. And so our electron picks up a small magnetic charge of their sector, and their electrons pick up a small magnetic charge of our sector. Of course, the mass term actually turns out to be pretty horrendous because you go from the sort of local, well, in this case, I just wrote it as a straight mass term, so I wrote it like a Stuckelberg mass. But it becomes a horrendous non-local mass. But, oh well. Okay.
Is there a CP violation implicit in this?
So the statement is, you can, if you just define CP as normal, there is CP violation. But there's a conserved symmetry, which is essentially CP times a Z2 in the other sector. Since, in some sense, right, there should always, the other sector preserves CP, and so this is just a redefinition. And so there should be a version of CP that's preserved here. And so it's a CP times a Z2 that's preserved instead.
Is this something that's testable, though?
Not as far as I can tell. Because in some sense, it really is just a field redefinition, and so the theory should be exactly identical.
So what would you get if you had the FF dual mixing, but you had the regular dark photon mass?
Then you would actually get a theory where they both just look like they're electrically charged and not magnetically charged. And I will actually, in 2 or 3 slides, get to sort of the physical picture of why this mass term is important. Because, this mass term will actually be pretty important. It was completely useless so far, right? Nothing I've said so far actually depended on the mass term. But later, when you try to calculate physical quantities, it'll actually show that the mass term is pretty important. So maybe I'll just punt on that for now and then talk about it a little bit more later.
And do you have any real, in this formulation, do you have any real precise idea of what this mass term does, or is this sort of...
Well, what it does, you can just go to the other picture and then do everything in that
but
picture.
In this picture,
in terms of like what's the non-local form and what it looks like, no, not really. It's pretty horrendous.
There are local Lagrangians you could use to describe it.
Yeah.
So it's time to look at Schwartz and Sen and tell you the answer.
but I'm not going to get any physical intuition here and now.
Yeah.
I'm just being told to look at some complicated paper.
Yeah.
And-
Hopefully
but
later
I'm-
I'll sort
but
of
you
give
can't
you.
distill for me anything about what that term is somehow?
I think I might have an answer that will somewhat answer that in like 2 slides.
Okay.
So give me a quick moment. So, yeah, so if you apply the E and B rotation to the previous picture, what you get is that our electron picks up a small epsilon charge under them, and their electron picks up a small epsilon charge under us. And then you say, well, okay, everything is an electron, so it can be light, but there's still these sort of fundamental electric charges that sort of magnetic charges that appear. Okay, so now we'll sort of try and talk about the physical picture of this guy, right? I'll get to, and in particular, you'll see why this mass term is extremely important. So what is sort of the physical picture of this guy? Well, let's imagine adding doing the mass term by a Higgs mechanism, and you'll have some charge assignment table like this. And so what you see is that, well, the dark one is Higgs, and it has monopoles. And so we know what Higgs monopoles look like. They're confined, right? We know confinement and sort of Higgsing are dual to each other. And so this is what the mass term does. It takes your monopoles, it makes them so that they're confined. And so just like QCD, there are going to be strings connecting monopole, anti-monopole. And so sort of what you see is just that, well, the monopole, anti-monopole just look like this. All physical objects are finite energy physical objects, sort of the equivalent of protons and neutrons, is this whole combination, and you notice that it has no Milli-magnetic charge. And so you get around the quantization of angular momentum exactly the same way as QCD. So this is sort of the picture of them. And sort of to drive this point home of why the mass term is important, let's go to the case where the dark photon mass is irrelevant. All right, so let's pretend, for example, that the mass term for this other guy is 0. And now let's calculate the force between an electron and a monopole. Well, the monopole electron has 1 here and epsilon here, and so the electric charges and magnetic charges that it generates in the other sector are just epsilon times their R sector. But now this monopole has minus epsilon 1, so it sees minus epsilon times our E field plus their E field. And so notice that the effective E and effective B fields felt by the monopole is nothing, at least in the limit where the mass is 0. And so in some sense, it's like, yes, it does look like this.
Sorry, why is B prime non-zero for the electron if it has 0?
If it's moving, then it'll generate a B field for that.
Okay.
And so you just say, but you know that their B field is always exactly epsilon R's if you're generating R B field with moving an electron. So the only way to actually get a force between these two guys is if one is moving, because there's always a V cross B.
I got it.
And so, yeah.
Okay.
But you'll notice then, because you have to add these guys, and monopole is a minus epsilon, it's actually 0. And so there's actually no force between the monopole and the electron in the limit where there's no mass. In other words, there's no real sense in which, physical sense in which this thing acts like a monopole then, right? So what about in the case where the mass is non-zero? Well, we're talking about B fields in a superconductor. We know the answer to this question experimentally. The B field is exponentially screened by the mass. And so now when you look at the effect of B, it's actually just epsilon B times this guy here. And so you'll notice at very close distances, when R is about 0, you get 1 minus 1. There's no force between the two. But when you're far away, in particular at a distance scale larger than 1 over m, the dark field, this guy has been screened away, and so then it does look like it has an epsilon charge. And so this is sort of the way in which it sort of you physically reconcile all your different interpretations, which is that at close distances it does not look like a monopole, but at long distances it does look like an epsilon charged monopole. And notice that distance scales where it actually looks like a monopole is 1 over m, and that's also the string, the characteristic energy scale associated with the string. So at that point, it also looks like it has a physical Dirac string on it, and then you can be like, well, that's how it got around all the problems. associated with quantization of angular momentum and whatnot. Okay, so it might have been a bit fast, but hopefully I have made convinced you guys that it's at least plausible that these sort of millimagnetically charged particles exist. I would say sort of just look at kinetic mixing with monopoles, and then they just pop out at you, right in your face. So then, what are the constraints on these guys, right? Because people don't usually talk about them, and so there are a lot of different. You have to sort of think about what are the constraints associated with them.
So the string tension is given by the mass.
Yeah. Everything about the string is associated with it is basically the mass. So the tension is of order the mass, and yeah. There's one scaling problem, so everything has to be that scale. You can actually make it precise by saying this is a tough polyfault monopole, and then you Higgs the U1, and then you have an what is it, like Nelson-Olson string between the two monopoles. You can calculate everything in that particular example. And that's exactly what you find, that the tension is the mass squared. Okay, so what are sort of constraints on these guys? Well, there are two things you can do. The most work has sort of been devoted to if the magnetic charges already exist around us. There are a lot of things. There are like experimental constraints, like looking for monopoles in rocks. People have done things like that. There are also a lot of astrophysical constraints. And it actually turns out that if magnetic charges are already abundant around us, there's one bound which is essentially the strongest one. And it's called the Parker bound. And so the idea of the Parker bound is as follows. Well, if you put a magnetically charged object in a B field, it accelerates. Conservation of energy says that the energy for that acceleration came from the magnetic field, so the B squared energy density. And so if you just have monopoles in our universe, they'll be accelerated by galactic magnetic fields, and they'll suck out all the energy density that are in our galactic magnetic fields. And so the very existence of galactic magnetic fields places a bound on the flux of monopole-like objects, like magnetically charged objects. And so they've calculated this, and it's basically some number here. And it turns out to be basically the strongest bound that we have available, essentially at all. But this is assuming that they exist already.
Sorry, but is this, go ahead, Mike.
Go ahead.
This doesn't depend upon the magnetic charge?
So this is the magnetic flux in the universe. So this is a bound on Q times the number density.
Oh, okay.
Yeah. So if you divide by Q essentially if you want to put a bound on number flux.
Yeah, I'm a little confused because, so this is analogous to saying, suppose we lived in the universe and we observed electric fields. We could
Yes.
somehow say there can't be too many electrons.
That's right.
But I'm just confused about that because if there are no electrons around, I would have to pair create them, and I would need a very strong field to pair create them, and that field would depend on the mass. So what's really the assumption here?
This is the assumption that you just had monopoles around already. You didn't say how they got created or anything like that.
And
You
the
just say
sign doesn't matter?
the sign doesn't matter. It's just whether they get accelerated in the plus direction or the minus direction.
Right.
Either way, they take energy out of your B field. Right.
Let's see, if you have pairs of monopoles, as long as they're widely separated,
Yeah.
it doesn't change anything?
Nope. Because as long as they're not annihilating with,
Right.
then let's say you just had a B field in the same direction across the entire universe, then all plus monopoles will be way up there and all minus monopoles will be way down there. And so they can't annihilate, they just all keep on sucking energy out of the B field.
I guess I'm just thinking of something, maybe it's too simple, but if I just have a constant electric field in one dimension,
Yeah.
and I have an electron, and the electron just accelerates,
Yep.
I don't see the electric field. How do I see the
In
electric
2D,
field?
it's very simple because when you have E, an electron, E minus E. on the other side. And you can see that you use the energy, as you take the electron to infinity, that everything is to the right of the electron, and so it's now all E minus, or electric field minus little e. Right?
Yeah, okay. That makes
And so in 2D, that example is extremely clear. In 4D, it starts getting a little messier because you have to say,
No,
I get the
okay,
electric
okay.
theme by putting plus electrons here and minus electrons there, or positrons to electrons, and then you start annihilating electrons as you decelerate up, and so the E field gets neutralized that way.
Okay.
Yeah. And for monopoles, it's even more complicated because you have to talk about EMFs, but it's essentially the same thing. Okay. But yeah, because of conservation of energy, you know that it has to come from the
Yeah,
E and
no, I
B
just
field. It's
wanted
just the
to-
physical mechanism changes a little bit depending on if it's electrons or or monopoles and whatnot. Yeah. Okay. What about constraints on monopoles if they are not surrounding us, right? What if they're reheated to low energies? These guys were never created. So there are constraints. The zeroth order, I'd say we actually have no constraints on them because of the following, because we don't know if these guys are sort of extended objects or not.
So could we just go back to the Parker bound and
Yeah.
trying to understand the
Yep.
implication? So this is the bound on the flux, which is the charge times the
The
number
number
density.
density, that's right.
So if the charge is really tiny,
Mm-hmm.
small mixing.
Yeah, the number density
number
can be
density
huge.
is huge, and so would you know that?
To zeroth order, no. Because
It's not
because
real
as you take epsilon to small, it's a lot harder to observe. And so almost all physical quantities you want to calculate in like the scattering and whatnot turns out to be proportional to the charge times the number density.
Right.
And then in fact, as you take epsilon smaller, you deposit each scattering deposits less and less energy, and then you start getting pushed below experimental energy deposition, resolution, and whatnot. And so it's
So in what sense is this a strong bound? So it's saying that
it's just when you it's a strong bound if you compare it to just looking for monopoles in other ways. If you look at those monopoles and be like, I'm looking for scattering, or I'm looking for monopoles in
yeah, well,
rocks.
that's what I'm trying to compare it to. Yeah.
Most of those will also be proportional to this exact flux.
I see.
Because if you're looking at scattering, right, it's the probability, it scatters, deposits some energy, right, proportional to the charge, and then you multiply it by n sigma, and so in fact sometimes it gets worse.
I see. So that's,
Yeah.
that's always weaker than this.
It tends to be weaker.
I see. Okay.
I think that statement I made though is I also made I assumed that was a minimal like Dirac charge monopole. So for those cases, it's definitely stronger. I don't know if I haven't looked at the case where you take Q goes to infinity, and so I don't know if in that limit is this also the strongest bound or not. But definitely for minimal, like the Dirac charged monopoles, this is the strongest bound on the number density.
I mean, how far away is the other kind of bound? Direct
Only a few
experimental
orders of magnitude, like two or three
bound? So
orders
it's
of
possible
magnitude.
to
So it's
do the
possible as
experiment, the direct
I'm not 100% sure. I haven't looked into exactly how these things scale with modern technology. Most of this was done in like the 90s, or like 10, 15 years ago.
Mhm.
So,
Okay.
yeah. Okay. So first, let me convince you that if these guys are Toth polycalled monopoles, we essentially have no bounds on them if they don't already exist. So if these guys are sort of Toth polycalled monopoles, what do I mean by that? I mean that their physical size, like R, which is the size of all like the gauge boson distribution, like the hedgehog configuration, is a lot larger than 1 over its mass. And so this initially will then tell you that the production is exponentially suppressed. So what is in fact, to see that this must be true, let's consider the following limit. Let's consider the limit where R is something that's physically sized as like a table, and M is basically, let's say, a TV, the size of like the LHC beams. Then what you're basically trying to do is you're trying to pair produce these huge fluffy objects with very tiny beams. In other words, you're trying to do something that violates decoupling, and so this will be exponentially suppressed as a result, right? Quantum mechanics says that everything that can happen will happen, so the answer is non-zero, but there's always an exponential suppression associated with these processes. That's basically proportional to the ratio of the different length scales involved. So in fact, like in all the cases where anything is exponentially suppressed in quantum mechanics, you can just look at the difference in length scales and see it that way. Of course, you don't get factors of pi in order 1 or 2 correct, but this will always give you the parametrics. So, so if these guys were Toft-Polyakov monopoles, then their cross-section should be exponentially suppressed, and we basically then cannot constrain them because you can never produce them. And so, yeah, so exponentially suppressed production cross-section means no constraints. So, as of right now, there are essentially no model-independent constraints on these millimagnetically charged particles because they could be exponentially hard to produce. So, my goal is basically to obtain model-independent bounds on these guys, but perturbative production can potentially be exponentially suppressed. So I need something non-perturbative-like, right? I need something that basically has a large number of initial states or something like that. So
maybe you're going to address this, but what if you have clouds of these things?
Yeah, so that's essentially how you're going to try to produce them. You have like a huge cloud of photons, and then you scatter them together to create your monopoles.
Okay.
And so, what is a huge cloud of photons? It's large electric and magnetic fields. And so you probably see where I'm going with this, that you essentially get Schwinger pair production. And so Schwinger pair production occurs for both electric and magnetic particles in strong electric or magnetic fields, respectively. Schwinger basically calculated this a long time ago. Affleck and Manton generalized it for a monopole. And it's essentially the same formula, and I guess I was a little stupid. The difference in 4 and 8 here is because Schwinger did it for a fermion, Affleck and Manton did it for a scalar. If you do it for a fermion, or if you do Schwingers for a scalar, that accounts for this factor of 4. And so it literally is exactly the same answer, with the identification of the magnetic charge being 4 pi over E. Okay, so this is sort of the formula for Schwinger pair production. And as I said before, every exponential in quantum mechanics can be understood by comparing ratios of the size of things, right? And so let me argue that this exponential has to be m squared over the electric field. Just by some physical thing, where m is, of course, the mass of the fermion. So let's look at the 2D example. The 4D is slightly more complicated, but gives exactly the same answer. So let's consider 2 equal energy configurations. One where the E field is just everywhere E, and then the same configuration where you spontaneously nucleated an electron and positron, some distance d apart. And because you've nucleated them, the equations of motion say that the electric field inside is smaller. And so conservation of energy says that the E times the electric field times the distance is 2 times the mass. And if you're doing this in 4D, this is basically the dipole energy, the energy of a dipole in a magnetic or electric field. Okay, so this tells you what's the typical length scale, D, associated with Schwinger pair production.
But this is without the Milli-charged.
This E can be whatever number you want. So I'm just going to choose it to be, in the case of magnetic field, it's an epsilon.
Okay.
Yeah. So the length scale here associated with Schwinger pair production is just the mass over the electric field, or when epsilon is important, it'll be important that the epsilon appears here. And so, but what is sort of the quantum mechanical fuzziness associated with the electron? They're being produced at rest, so the quantum mechanical sort of fuzz associated with the size of an electron is just 1 over m. So you can sort of guess then, if you just had to naively guess what would be the answer of Schwinger pair production, Well, if the distance is this guy, if the distance is much larger than the fuzz, then you'd say it's exponentially suppressed. And it's only when this sort of distance associated with Schwinger pair production is much smaller than the sort of this fuzziness of the electron are you able to proceed quickly. And you'll notice that that's exactly what you get here. This is exactly this distance over the Compton wavelength, like 1 over m. And so, yeah, so this is exactly the physical understanding of why this guy is suppressed by m squared over the electric field. And then this guy, E squared here, is determined just by dimensional analysis. You don't get the 4 pi cube, but oh well. Can't ask for everything, or can't get everything. So, of course, I want to apply Schwinger pair production to the case where my monopoles are connected by a string, or the case of QCD, for example, where QCD quarks are connected by strings. So how does this guy change? It turns out, basically, you can do the pair production calculation again. And what appears here is basically now just m squared over electric field minus the tension squared, ma squared. So essentially, as long as the mass of the dark photon is small enough, or the tension of the string connecting the monopoles is small enough, then you basically don't have a problem.
If you have this other scale, which is the if you like the compositeness scale of the monopole, its radius. Doesn't this formula also require that the distance scale is larger than that radius?
So
if that radius
that
is
appears,
large,
yes,
then you
that is
start
true.
suppressing it more.
And the way it actually ends up becoming important is if you look at Affleck and Manheim's formula, there's a plus g squared, which then if you calculate when does this exponential become 1, it turns out to be exactly at the radius, which is predicted by the 2th polygon monopoles. And so for electrons, this e squared is small, and so it's unimportant. But for monopoles, this g squared is large, and it turns out to be important, and it becomes non-exponentially suppressed just when the distance becomes the physical size of the monopoles.
This effect is making I'm confused.
It's
because this
enhancing,
is making the probability larger.
Yep.
I would have thought intuitively that you make your estimate for D based on the just the energetics.
Yeah.
But then if the monopole was much bigger than that, you're trying to create a state which is the same kind of argument as the perturbative production. You would expect it to be very suppressed there, right?
So I guess the statement is,
so
in that case, what actually happens is what dominates is productions of monopoles not at rest, because then they start shrinking, right, because of boost factors and whatnot, and you still get pair production. Like, for example, if you estimate what is the typical energy of the electrons being produced, it turns out to be basically the energy.
How does boosting them happen? I mean, there's still. You're saying because it flattens them?
It flattens them, and so then the distance becomes small, and the calculation is okay again in that limit. But in all cases, you lose perturbative control once the distance scale becomes of order the size, because that's when the exponential disappears, and then your standard Coleman instanton calculations are just not valid. Yeah, so these formulas are only valid in the region where it's exponentially suppressed. And then in the region where it's not exponentially suppressed, you just don't know really what it is. By dimensional analysis, you have to say it has to be proportional to e squared, but the coefficient, we have no idea.
I mean, I would have said, I'm not sure if we're agreeing or not, I think I would have said these formulas are valid when the distance scale D is much larger than R.
Yes,
and then everything is fine.
That's equivalent statement.
That's equivalent, okay, good.
Yeah.
Okay. Thanks.
Okay. So, Schwinger pair production means you can sort of give a large production of these millimagnetically charged particles if there's a large magnetic field. So then, just like the Parker bound looked for the magnetic field of the galaxy, let's just look for the strongest magnetic fields we know of. And then their very existence will tell you something, will constrain these guys. So the largest magnetic fields in the universe are magnetars. And then you can use these magnetars to constrain these new particles because Schwinger pair production neutralizes magnetic fields. And so the very existence of a magnetic field this large, of order the some size, will tell you a bound. Essentially, that Schwinger pair production is not happening. And so I'm going to assume people don't know much about magnetars. So let's give a brief review of what magnetars are. They're the strongest magnetic fields in the universe. They are neutron stars, in particular are pulsars. Their size is about 10 kilometers, which is almost their Schwarzschild radii, right? Neutron stars are an extremely compact object. The magnetic fields are about 10 to the 15 Gauss, which is of order capital MeV squared. And so these are pretty ginormous magnetic fields. Their age is about 10...
Do they know why they have magnetic fields?
No. They don't even know the answer for why neutron stars have magnetic fields this large. Okay, so for the magnetic fields of the neutron stars, they have an explanation that's not really an explanation, which is if you take all the magnetic field of a star, compactify it into a neutron star without losing any magnetic flux, you get, roughly speaking, the magnetic field of a neutron star. Magnetars have magnetic fields that are like 3 or 4 orders of magnitude larger, and so they have no idea how these guys obtain their magnetic fields. So yeah, we know extremely little about these guys. So their magnetic fields are MeV squared. Their age is about 10 to the 4 years.
How do you know that?
Okay, so there are two ways. One, they look at P dot over P, where P is the period at which these things spin. So they're pulsars, so you can measure their spin. And so that's one thing. The other way is we only see them in sort of star-forming galaxies, which are very young. And we know from just studying the stars that these galaxies are always at most 10 to the 4 years old. And so by association of where they appear is another way of getting this 10 to the 4. But by themselves, they have no idea. Their luminosity their dominant source of luminosity is in X-rays. And it's about 10 to the 35 ergs per second, which there's a numerical coincidence here, which is equal to B squared V over T. B squared is the energy density, magnetic field, the size, volume, and the age, 10 to 4. This is what leads people to say that magnetars are actually powered by their magnetic field. Like their energy loss is dominated by their magnetic field. They have no idea how this luminosity occurs. But
So
this
this is
coincidence is why they say this.
From the age argument, the argument by association, it's a coincidence, but the other one, it's a definition, right? If you just say
Yeah.
at what rate of they're losing power, they can't be older than that if you're
Yeah.
saturating it.
That's
So
right.
it's the statement that those two things agree. It's
Agree,
the
yeah.
same statement.
That's right.
Mhm.
And so, essentially because of this numerical coincidence, people say that they're powered by their magnetic fields, but we have no idea really how the magnetic fields power anything, especially since we have no idea how they get these large magnetic fields. There's about 20 or so observed, and they're of order kiloparsecs away, so they're very close objects. And aside from what I just said, there's nothing to know.
How's the magnetic field measured?
I will get to that.
Okay.
Okay, so the way we saw them so far is basically they're anomalous X-ray pulsars. This anomalous just means that they are X-ray pulsars that are not powered by the standard means. Standard means are the I omega squared, the angular momentum, and the other is accretion. And it's just been shown looking at them that it's not angular momentum and it's not accretion. Neither of those can account for this. The other way we see them is through soft gamma ray repeaters, and essentially sometimes, occasionally, with no real periodicity, we'll see huge gamma rays from these guys. And their peak luminosity is larger than the Eddington limit. And yeah, so this was the way they originally saw it, and then they also discovered there were anomalous X-ray pulsars. And so since the magnetic field is really important, I should really tell you guys why we think the magnetic field is what it is. And so the magnetic field if you talk to a pulsar or magnetar people, they'll give you a really complicated argument. They have numerical simulations for how these soft gamma ray bursts happen, and the time scale associated with them is associated with magnetic instabilities of the magnetar. And by studying these pulses, you can find the magnetic field. Of course, this gives us very little physical intuition for how we see the magnetic fields. So let me give you a really crude estimate for how we get the magnetic field. That gives you within order like 5 or 6 of the correct answer. So what is a magnetar? Well, you can imagine it as a spinning dipole moment, right? We know that some currents and whatnot are generating a dipole moment, and it's oscillating. And so then we just go tell a freshman physicist to calculate what's the energy lost in electromagnetic radiation. This comes at the expense of the I omega squared, right? The angular momentum of the sky. And so by setting those two equal, you just get that the B field is essentially 10 to the 15 Gauss. When you put in observed values of what the period is, how fast the period is changing and whatnot. And so this is sort of the really simple and crude way of getting the magnetic field.
So you're just saying that you're explaining both its period and its derivative by electromagnetic
Or
radiation.
in particular, how the period is changing with
Yeah.
time. Because the energy emitted by electromagnetic radiation obviously has to come from the angular momentum of the object. And so
But what's observed somehow is these pulses. So the idea is that somehow this is some averaged version of that.
So what you see, the pulses have nothing to do with, are not the dominant energy loss. The pulses let us measure the period with extreme precision and the period dot with extreme precision. And that's what we use. But you can actually also estimate what's the energy in these pulses, and they're orders of magnitude smaller than the other.
But the numerical simulations are somehow using the pulses to argue this in a complicated
yeah.
way.
So then
But then shouldn't there just then be a more complicated version of this same estimate? Or you say?
So the pulses that they use to estimate the magnetic field are not the pulses that you just typically see in the pulsar. It's just additional instabilities that just over time just happen and then emit huge gamma rays.
But their simulations should also
Their simulations also give this as well, yeah.
Okay.
It's just that I think the main reason why they don't say that this is a very good way of measuring it, like the way that they would argue for not doing this, is because one, we don't know too well what this angle is between here and there. And so that's one thing. And the second is that there are various other things that can cause you to slow down. Like if there's a tiny bit of accretion onto the spinning guy, it'll spin it down, but it's not due to electromagnetic radiation and whatnot. And their claim is that these pulses give a much cleaner environment way to measure it. And I just have to trust them on that. But those are the words they tell you. Okay.
But I mean, a fortiori, this sort of seems to say that this is a dominant energy loss.
Yeah, that's right.
Right. If you believe their simulations.
That's right. These X-rays that they emit are basically due to this, like rotating a dipole. Okay. So, given that we don't really know very much about the magnetars, I'm just going to approximate them as the following case. I'm going to take them as a radius of 10 kilometers. They're going to have a uniform B field of 10 to the 15 Gauss. So this is MeV squared. And their age is going to be 10 to the 4 years or so. So I'm basically just going to approximate this as the following. There's a sphere of 10 to the 10 kilometers. Inside there's a uniform magnetic field that's of order MeV squared. And then Schwinger pair production can happen here. So if the B field is of order MeV squared, the B field, effective B field, is going to be screened because remember, as I mentioned before, you have to be far enough away from where the magnetic fields are being generated. So as long as m is essentially larger than 1 over 10 kilometers, what you'll be seeing is basically the full magnetic field, and you won't be in this region where the B field hasn't been screened yet. And so, let's say you produce a pair of monopoles. How much energy is carried away? Where it's just force times distance, right? The force is charge times the B field, and then the distance is basically the size of the object, 10 kilometers or so. And so this is about how much energy is lost per monopole. And so you can calculate the energy taken away from the magnetic field as a function of time, as a function of dV, by basically taking the Schwinger pair production formula, multiplying by the energy lost per pair production, and seeing that's smaller than basically B squared over T. So in other words, this is just the statement that the magnetic fields have survived until now. And so, of course, what you can do is then just now just make a plot. Essentially, what happens is the bounds cap off at around 10 to the minus 18, and at around masses at around 10 to the 3 or 10 to the 4, 10 to the minus 3 of EV, they start growing up. So here what happens, I guess I'm showing 3 different plots. This is basically, I said, if the mass is larger than about 1 over 10 kilometers, then you're insensitive to the mass of the dark photon, or the tension of the string. And as you increase the tension of the string, the bounds become weaker and weaker, because the effective B field you feel is smaller and smaller. And so the reason why there's a line here and then a flat line here is here you have the exponential suppression. This is where you basically just run up against this exponent. So Schwinger pair production is exponentially suppressed. And so that's what kills it as you take m large. But you'll notice that you can actually get to masses of about 10 of about MeV or larger. In fact, this bound hits all the way up to GeV, because the magnetic fields are so large that you can even live with a small exponential suppression. And then here what happens, the reason why it gets capped off is because the energy loss is too small. Right? As the charge goes to 0, they carry away less and less energy. And so at this point they just stop carrying away enough energy. Okay.
You're saying there's some region of this parameter space where these magnetars are creating TeV mass particles.
I guess GeV is
GeV.
about the best it gets.
Okay,
Yeah.
GeV. But still, that's 3 orders of magnitude bigger than the magnetic field.
Yeah, that's right.
With sufficient rate to actually
To destroy the magnetic
destroy
field.
these things on the time scale that we've seen them.
Yeah, it's the numbers are quite huge, so you can take some exponential hit.
Okay.
Yeah, and then this is, for example, this 10 to the minus 18 numbers to be compared with, let's say, bounds on milli-electrically charged objects, which are only at 10 to the minus 13 or so. This is basically 5 orders of magnitude better than bounds on electrically charged objects. So it's quite amusing that, at least at low energies, they're that much better. So, to conclude, people very often will talk about milli-electrically charged objects, but you can always also talk about milli-magnetically charged objects. There's no real obstruction to it. And because magnetically charged objects could be let's say the Hooft polycalled monopoles of the dark sector, there are no real model-independent bounds on what they can be. And so, what you can say then is, it turns out that if you look at magnetars, Schwinger pair production happens both for extended objects and for local objects. The rates are basically the same. And what you see is that just using the fact that the magnetic fields exist in nature. And it doesn't matter how they're generated or anything like that, just the fact of their mere existence places extremely strong bounds on these sort of magnetically charged objects that are quite like 5 orders of magnitude stronger than any bounds we can place on electrically charged objects. All right, thanks.
I'm just trying to get a picture of the following thing. I mean, normally you introduce kinetic mixing just between two U1s, not the magnetic bit.
Yeah.
In order to have some kind of twin model that helps the hierarchy problem and all
that's
this, right? So first of all, does this in any way help the hierarchy problem?
No, it doesn't.
It doesn't, yeah. Okay.
Yeah.
I guess then the rest of my questions are irrelevant. Okay.
I mean, I think the way I would phrase it is, if you normally have kinetic mixing, then I think it's quite logical to write down also FF tilde mixing.
Mhm.
And then FF tilde mixing has the exact same effect of generating small magnetic charges. And so if you think it's okay to look at kinetic mixing and have electrons, then you should say it's okay to have this magnetic mixing with electrons. Or you can say that's kinetic mixing with monopoles, but that's
But there must be some
language
kind of
choice.
symmetry that would forbid the CP or something
Yeah.
that would forbid the FF rule.
That's
So-
right.
So if you said.
So you can, if CP is a good symmetry, you can forbid FF dual, but not kinetic mixing. But of course, CP is not a good symmetry of the standard model, so you have to wondering, well, that means at some level of loops and whatnot, it will be generated. And so why not just take it order 1? Well, the number of loops has to be smaller than 10 to the minus 18, so you can take quite a few loops and still be constrained. Of course, then you also need like the electrons in the other sector to be this slight, but yeah.
Just a quick comment before we go. So if anybody's interested in joining for dinner, talk to me. Okay?
Yeah, there's something I was confused about. It's how U1 can be confining. Because usually you need SUN
Yes.
for
It's,
confining.
well, do you agree that you can Higgs the U1? Do you agree that you can Higgs the U1?
Yes.
Then you can then by electromagnetic duality, that's the same as confinement. So in particular, you can go to something, let's say, you can make this precise in the limit of something like, say, n equals 2 SUSY, where you take something Seiberg-Witten-like, and there you can show that you actually, by adding small mass rooms, can explicitly show that Higgsing in the electric sector is equivalent to confinement of monopoles. And so, yeah, so that's essentially how you have to do it. I guess the reason why you're probably not familiar with it is people usually don't talk about monopoles. And so it is true that Higgsing will not cause the electrons to condense, to confine, but it will cause the monopoles. And there are several explicit examples that you can show this.
So that's maybe also a way of saying why that magnetic mass is so weird. Right?
Yeah, that's right.
Because it's somehow a confinement, it hides confinement for what you there call the electric field.
Yeah. So yeah, when you try to call it an electric field, then this mass which causes confinement is non-local. It's a huge mess. It depends on how you express it.
Depends whether the Higgs field has electric charges.
Yeah.
All right, let's thank Anson again.